All right, so imagine you're trying to teach a robot how to walk. But instead of programming every little twitch of every joint, you just give it a little nudge. You tell it good job when it manages to stay standing and whoops when it tips over. That's basically the idea behind reinforcement learning. It's this really cool branch of AI all about teaching machines to learn from the consequences of their actions through pure, unadulterated trial and error.
So that brings us to the big question, right? How in the world does a machine learn to master something ridiculously complex, like a strategy game or a robot's movements, when it doesn't have a textbook, it doesn't have an answer key, it has no teacher? Well, that's the puzzle we're going to unpack today.
So here's the game plan. First, we're going to get a feel for what it really means to learn from experience. Then, we'll look at where this stuff is already working behind the scenes in your life. After that, we'll pop the hood and break down the core engine that makes it all tick. We'll even take a quick look at its surprisingly weird history before we wrap up by looking at the road ahead. Sound good? Let's dive in.
Okay, let's start with that fundamental idea. What does it actually mean for a machine to learn from experience? Honestly, the best way to think about it is like a toddler learning to walk. It's all about just trying stuff. You stumble, you fall, you get feedback from the world, ouch, the floor is hard, and slowly, step by wobbly step, you get better. And this slide is a perfect way to visualize the difference. On one side, you have the map reader. It's like giving an AI a perfect GPS with step-by-step directions. It just follows the instructions. That's kind of like a lot of traditional AI. But on the other side, that's reinforcement learning. It's the Instinctual Explorer. It gets dropped into a maze with no map. Nothing. It has to learn by bumping into walls, taking wrong turns, and eventually just happening to find the exit. It's not following a script, it's building its own gut feelings. It learns by doing. And look, this whole Instinctual Explorer thing, it's not just some clever analogy. This is a super powerful technology that's already shaping the world around you. So let's talk about where you might be bumping into reinforcement learning without even knowing it. I mean, the applications are all over the place. You see it in gaming, creating AI opponents that are so good they can literally learn your playstyle and beat the best humans on Earth. Those product recommendations or ads that seem to read your mind, yep, that's often RL, learning from what you click on in real time. And it's not just for fun and games. We're talking about huge fields like healthcare and robotics, where it's helping discover new treatment strategies and teaching factory robots how to deal with the chaos of the real world.
But maybe the most famous, the most mind-blowing example has to be AlphaGo. Back in 2015, it did something that experts thought was decades away. It beat a world champion at the game of Go. And you have to understand, Go isn't like chess. It has more possible moves than there are atoms in the universe. No joke. So this wasn't just a game. It was a massive, massive moment for AI.
So how did it do it? What was the secret sauce? Well, this quote right here just nails it. The key is that AlphaGo wasn't programmed with strategies from human masters. Instead, it played millions and millions of games against itself. It was its own sparring partner, its own teacher. It just kept experimenting, learning from its own blunders, and inventing strategies that no human had ever even dreamed of. It literally surpassed centuries of human knowledge by teaching itself.
Okay, so we've seen the what. Pretty cool, right? But now let's get into the how. Let's pop the hood and look at the engine that makes all of this possible, the core feedback loop that drives the learning.
It all kicks off with something called the state. And that's just a fancy way of saying a snapshot of the world at one specific moment. So if our AI agent is in a maze, the state is just its current coordinates on the board. Simple as that. It's the where am I right now part of the puzzle.
So you know where you are. Now what? Well, you have to do something. You have to take an action. And in our maze example, that's super straightforward. You can go up, down, left, or right. That's it. This is the what are my options part. But here's the key question. How does it know if moving north was a good idea or a terrible one? That's where the reward comes in. It's just feedback from the world, a score. Reaching the end of the maze might be a big plus 100 points. Hitting a wall? That could be a -1. And this number, this simple score, is literally the only guidance it gets. It's the North Star for the entire learning process. And finally, all of this comes together in what's called the policy. You can just think of the policy as the agent's brain or its strategy map. It's the rulebook that looks at the current state and decides which action to take. And the whole point, the entire goal of reinforcement learning, is to tweak and improve that policy over time to get the biggest possible reward. Okay, so let's put it all together in this loop. It's actually pretty simple when you see it laid out. Step 1. The agent looks around and observes the state. Where am I? Step 2. It consults its policy, its brain, and picks an action. Okay, what should I do? Step 3. The world gives it a reward. Was that a good move or a bad one? And here's the magic. Step 4. It uses that reward to update its policy, to tweak its brain just a little bit. And then it does it all over again. And again, and again. Millions of times, getting a tiny bit smarter with every single loop.
So, now we have the how, but what about the where? Where did this whole idea even come from? And this is one of my favorite parts of the story, because modern reinforcement learning didn't just pop out of nowhere. It's actually the result of two totally different fields of study that for decades had absolutely nothing to do with each other. So check this out. On one track, you've got trial and error learning, which came out of psychology, studying how animals learn way back in the early 1900s. And on a completely separate track, you've got engineers in the 50s developing something called optimal control. For the longest time, these two worlds never met. It wasn't until the late 80s that researchers finally put two and two together and merged them to create the field we have today.
And if you want to know just how deep those psychology roots go, listen to this. This isn't from some AI textbook. This is from a psychologist named Edward Thorndike writing in 1911. He called it the law of effect. Basically, if you do something and something good happens, you're more likely to do it again. I mean, think about that. That simple idea, first observed in animals over a century ago, is the exact principle that powers the most sophisticated AI today. It's just wild.
So those big ideas eventually got turned into a whole toolbox of actual practical algorithms. Now don't worry about memorizing all these acronyms. Q-learning, PPO, DQN. Just think of them as different recipes. They're all different strategies for an agent to take that reward signal and use it to update its policy. This is the nitty-gritty engineering that takes that simple law of effect and turns it into something that can solve real-world problems.
But of course, taking these amazing tools from a clean, perfect simulation into the messy, unpredictable real world, well, that's a whole other story. So for our last section here, let's zoom back out and talk about the big challenges, the major hurdles the field is working to overcome right now.
There are a few big ones. First up, data efficiency. Reinforcement learning agents are hungry for data. They might need to try something 1,000,000 times to get it right. That's fine inside a computer, but you can't have a real robot fall down 1,000,000 times. Second is something called reward design, and this one's tricky. You might reward a cleaning robot for picking up dust, only to discover it's learned to just dump the dust back on the floor so it can pick it up again for more points. And finally, there's that classic problem of bridging the gap between the simulation and reality.
And this example just hits the nail on the head. You can train a robot for thousands of hours in a perfect digital warehouse where it becomes an absolute master. But the second you put it in the real warehouse and someone leaves one single box in the wrong spot, the robot might just freeze up. It has no idea what to do because it's in a state it has literally never seen before. Closing that gap is a huge focus for researchers.
And all of this leaves us with a final and really critical question. The entire foundation of this technology is trial and error. The AI has to make mistakes. That's the only way it learns. So, what happens when one of those mistakes has real-world consequences? When a self-driving car that learned this way makes a tragic error on the road, who's responsible? The programmer who wrote the algorithm, the company that deployed it, or someone else? As these agents move out of games and into our world, that's not just a technical puzzle. It's one of the biggest questions of accountability we're going to face.